Welcome to a lesson with Dr. Powell. Let's look at how we can make functions or maps between vector spaces. And it comes from the idea of linear independence, and it results with functions that are describable by a matrix. So let's get started. Let's suppose that we want our domain to be R3. All right. And maybe we want our codomain to be R2. You want to create a function between these. Now let's look at R3. Let's pick a set of linearly independent vectors in R3, and let's do something that's simple and such that it spans all of R3. So we can represent every single element uniquely in R3 by a linear combination of those vectors. So these set of vectors will be a basis. Picking something simple, we can simply do 1, 0, 0, 0, 1, 0, 0, 0, 1. These simple vectors right here, they're linearly independent, and they span all of R3, and they're a basis. We call this the standard basis of R3, and these are the standard basis vectors of R3. Often we give these names. We call this like E1, E2, and E3 for the standard basis vectors in R3. The 1 simply means that the first coordinate of this vector is a 1 and the rest zeros. This 2 means the second coordinate is 1 and the other guy's zeros. And this 3 means the last coordinate is 1 and the other guys are zeros. Okay, so let's take any vector in R3 and let's see what can we do to send it somewhere. We want it to be sent to somewhere, and we want this to be a well-defined map here. So what we can think is every single vector v has a unique representation as a linear combination of the standard basis vectors, which are linearly independent. I mean, it has one and only one way of having these scalars a, b, and c that are real in order to be equal to v. There's only one way of doing that. So if we can look at this linear combination and think in particular, where does E1 go? Where does E2 go? Where does E3 go? We could really pick anything for these and then simply do this. Put A on there, B on there, and C on there. And this would be, whatever this is equal to, would be a well-defined function. Meaning that this definition only gives me one place where I could possibly send v, because I only have one representation right here of what v could be. If I had two different representations, then I'd have two different like sets of A, B, and C's describing v, and then I'd say, oh, where is that going to? I mean, does it go to this sum right here with the image of E1, the image of E2, the image of E3 with one ABC, or the other ABC, right? And so I might get two different places to send v. That wouldn't work. However, this is well defined, and I know exactly where to send v precisely because of linear independence. So because I have a basis, which is linearly independent, I can get a well-defined function just by defining it this way. In other words, the function really depends only on the images of E1, E2, and E3. So we can pick anything for those images, and those images do not have to be linearly independent or anything at all else. Whatever we choose, as long as it's in the codomain, it's going to make a well-defined map. So let's just pick a couple things. So let's do maybe like 1, 3, maybe 0, 1, and you know what? We can actually do the same thing again. It doesn't really matter. In fact, they all could have been the same. And this should be a well-defined map. This well-defined map is actually additive, and that can be easily checked. But for now, let's just take a look at how we can represent such a map, or such a function. All right, from R3 to R2. Well, we know E1 is sent to 1, 3, so we'll just write down 1, 3, and think in our minds E1 is being sent to 1, 3. E2 is being sent to 0, 1, so we'll write 0, 1, and think in our minds E2 is being sent to 0, 1. All right, E3 is being sent to 1, 3 again, so I think E3 is being sent to this. Okay, now if we just look at these numbers right here, the way we've listed them, this in a column, that in a column, that in a column, and we put parentheses right there, and we just remember that the first column has reference to E1, its image in the map, where it's sent to. Second one is where E2 is sent to, and the third one is where E3 is sent to. Then this describes the function. This describes the function of where to send V precisely. Let's think about this. See how we have 3 columns? That's because we have 3 standard basis vectors of R3. So kind of the 3 kind of tells us that our domain is R3. That comes from the number of columns. Now the number of rows, this is like the output of the function, like it's where is it outputting? What's the domain type or the data type of the output? The data type of the output looks like as 2 coordinates, so it looks like it's living in R2. So that's the codomain. So we got domain to codomain, just like that. And we know precisely where E1 goes. It goes there, E2 goes there, E3 goes there. Now, why don't we see where this function takes something else other than E1, E2, and E3? Well, let's represent, let's see, let's take a vector V, which lives in R3, just anything. Let's suppose that we take 2, 1, -1. All right, so 2, 1, -1. Now, these coordinates, 2, 1, and -1, actually turn out to be these coefficients, or these scalars right here. 2, 1, -1. You can check that that makes this hold. So what we do is we think of this as being a function, and just like function notation has like input on the right and moving to output on the left, like this, we input on the right here. So we put our input, we put it as a column, just like our outputs were columns here. So our input we can write as 2, 1, -1. All right. So let's see what our output would be. Well, this actually tells us exactly what the output is. It's basically 2 times this guy, 1 times that guy, -1 times that guy. And so in our particular case, let's just do that. Just remind ourselves that's 2, that's 1, and that's -1. So we could actually just go ahead and compute this, thinking, okay, 2 times 1, 3, and 1 times 0, 1, -1 times 1, 3. So but we're adding component wise. So just add the first components together. So we got a 2, and that's plus a 0, minus a 1. So that would end up giving us a 1. And then in the next component, we have so 2 times 3 is 6, plus 1 times 1 is 1. So 6 plus 1. And then we have minus 3. So that's 6 plus 1 would be 7. And then minus 3 would be 4. And let's see if we did that right. Okay, 1, 4. All right. So that's where it'd be sent to. So let's actually do this in columns to make this a little easier so we can see the components. Okay, if we had this be a 2, and then we wrote this as a column, 1, 3, and then we said plus 1 times 0, 1, minus 1, 3, let's see what's happening. So quite literally what we did is we took 2 times the first column plus 1 times the second column plus -1 times the third column, just like this. And when we add this up, it's like 2 times 1. So we're going to get a vector in the codomain. It's going to be an R2. So we get 2 times 1 plus 1 times 0 minus 1 on the top, which is, just like we said, was 1. And then 2 times 3 is 6. Plus 1 is 7 minus 3 is 4. And so we get something that, yeah, looks nice. I mean, we could have done this in just one at a time. We could have just added these two together. Notice this is just 0, 1. This is double this. So we could have thought, okay, 2, 6, and then we're just adding that one. So it's like 2, 7, and then we just subtract that guy off and gotten that. So we could have done it in any order here that we would like, but nonetheless, we were able to obtain the result. So a matrix is a function between vector spaces. It's an additive function. And not only is it additive, it's scalable as well, meaning that so it preserves addition, FA plus F of B. And so so it's additive, and it's scalable, meaning that if we scale before the map, it's like K is a scalar. It's the same thing as scaling after the map. So now a map that's both additive and scalable between vector spaces is what we call a linear transformation. And linear transformations between vector spaces, as long as they have nice bases that we can write things with respect to, can be written as a matrix. Thanks for watching.